Okay, so they told me to just start without any introduction. So let me just say that it's really fun to do this. I've given you kind of an overview of the standard model in my talks. And next Monday, you will hear from Heather Gray, who's an experimentalist on ATLAS. And she's going to tell you all the hard things you need to do to make these beautiful plots that I'm showing you. So today, I'm going to kind of switch gears a little bit and talk about thinking about the Higgs as part of a standard model effective field theory. And this follows on to Anisha's lectures, where somebody asked me, well, what effective field theory is this? And he said, oh, it's just a standard model. So when I think about the standard model as an effective field theory, I'm really just using the effective field theory techniques to kind of quantify my uncertainty about what's happening at these very high scales. And of course, you should know from Anisha's lecture that there are a lot of effective field theories out there. There's the effective field theory that I'm going to talk about today, the standard model effective field theory. But then there's another effective field theory, which is different, which you would use for, say, low energy physics when you were looking at B decays. And then there's the soft collinear effective field theory, which you would use when you were summing higher order corrections, perhaps to some perturbative rate at the LHC. So all in all, this is a very specific effective field theory that I'm talking about. Okay. So whenever you talk about the standard model as an effective field theory, you have to start with a plot like this. And this is a plot, which I'm sure you've all seen, which shows the search limits for looking for new stuff at the LHC. This is an ATLAS plot, but CMS has a similar plot. And what you see from this is that, wow, they've looked for a lot of stuff they haven't seen. But you also see that the limits, here's a TeV. So in many cases, the limits go way beyond a TeV. So it makes sense to look at the model just assuming that there's nothing below a TeV. So you can't use the standard model effective field theory if there's new light stuff. So it only applies in the specific scenario where everything is heavy. So anything new that's happening is assumed to be above a TeV. Yeah?
Sorry, I don't quite understand how to read this plot.
Well, it's just looking for pink elephants, green elephants, you know, whatever. So here are my pink elephants, here are my green elephants. Here's what is leptoquarks. Can I read this? I got to get up close. Excited fermions, heavy quarks, leptoquarks, dark matter, gauge bosons. So everything the theorists tell them to think about. So the mass of the new stuff, they look for it, and they exclude it up to the edges here. So it's all excluded over here. So pretty much everything below a TeV is excluded. Yeah? Which one is it? Okay, which one is that? This one is, what the hell is this? So this is some flavor changing thing. So it's looking for electrons, bottom quarks, and strange quarks, and 38 TeV. So this must be looking at flavor changing currents, where the limits are very, very good. When Wolfgang comes and talks about the B physics and so forth, he'll talk about stuff like this. And the idea is that the limits on these rare decays are so good that they correspond to high scale. Yeah, but it's indirect, yeah? I don't know. Doesn't matter. It's just looking for new stuff. I mean, the details don't matter on this. They're just looking for new stuff. Yeah?
What is the second column supposed to be the signal?
Is the what?
Is the second column supposed to be the signal that you're looking for?
Again, let me stare real close here. This guy? L gamma?
Yeah.
Yeah, that's the stuff they're looking for, which is supposed to be indicative of the whatever the model is. So you're looking for 4 tops, and then you're looking for the 4 tops in certain decay modes. So yeah, I mean, the point about this is what you guys are actually asking is there's a lot of fine print in this, right? There's a lot of fine print. If you're a clever model builder, you can probably evade these. Yes. But it's actually important to note that the reach for looking for new heavy stuff increases with energy because you need the phase space to make whatever you're making. So we're not actually going to extend our reach very much past what we have now because these are 13 TeV numbers. The LHC will go to somewhere around 14 TeV, so the reach won't go up that much. But on the other hand, we're going to have this huge basket of statistics by running for the next 10, 20 years. So we need to use the statistics to learn something new. Okay. So we're going to use an effective field theory framework. And it's really, really a simple framework. We don't make a lot of assumptions, which is why it's such a nice theory, and it's a good way to look at new physics. So the first thing we do is we assume that the gauge symmetry is the gauge symmetry of the standard model. So the gauge symmetry is SU3, SU2, U1, okay? And we assume there are no new light particles. If there are new light particles, this doesn't work. But of course, if there are new light particles, we should just go look for them. That's more fun. So the really big assumption is that we assume that the Higgs particle is part of an SU2 doublet. And that's what defines what we call the SMEFT. We don't have to make this assumption. We could just look at the Higgs particle as a singlet and couple it to everything. That would be a different effective field theory. And that effective field theory is what's called HEFT, if you've heard those words. So this effective field theory assumes that the Higgs is in an SU2 doublet. We don't have any indication that it's not, so it appears to be a pretty good assumption, but it is an assumption. But these are the only 2 real assumptions of this whole thing, so it's very powerful. So we say, aha, the standard model is a low energy limit of some effective field theory. So my Lagrangian starts with the standard model Lagrangian, and then we're going to say, well, maybe there's some small perturbations on this which are coming from very, very high scale physics. So we'll make a tower of infinite number of dimension operators. So here I've got 1 over lambda squared, 1 over lambda to the 4th, some coefficient functions, and then all the operators. So Anish mentioned yesterday that the dimension 6 operators, we know the number of them, 2, 2, 4, 9, 9, and we know what they are. We can write them down. We actually know all the dimension 8 operators too. So here we go. These operators are made up of only standard model particles, and all the new physics, everything interesting is in these coefficient functions. So there are a lot of operators here. I'm going to do a fit to all the data I have at the LHC, and I can't use all these operators. So you'll see that I have to make some assumptions to pick out the operators that I think are important, yeah?
I maybe know this, but why do we have 5 and 7?
That's coming on my next slide. Because, yeah, that's an important question, but you were snoozing when Anish told you that yesterday. That's why I put it in today, because it's kind of fun. So there are a lot of operators, so you have to choose your relevant set. But the power of the standard model effective field theory is that some of these operators talk to the Higgs sector and they talk to the gauge boson sector, or they talk to the Higgs sector and they talk to the top sector. So by putting together the data in the top quark sector with the Higgs sector, with diboson production and so forth, you can get really, really powerful limits on these coefficients. And now you say, what about the dimension 5? So let me just review how you count the powers, what it means when I say dimension 4, dimension 5, dimension 6. So a fermion has mass dimension 3/2. A scalar has mass dimension 1. A gauge boson has mass dimension 1. And a derivative has mass dimension 1. So the standard model's mass dimension 4. So for example, 3/2, 1, 3/2, it's 4. Okay, so that's how you count when you put things together. But now you say, what about the dimension 5 operator? Well, there's only one dimension 5 operator, and here it is. And it comes about because the left-handed lepton doublet has the same quantum numbers as the phi tilde. So there we go. And we'll have phi tilde. This is I sigma 2 phi. Just there we go. So we can put these 2 things together. L bar phi tilde, and we can make it a gauge singlet. So this is the only combination of gauge singlets here. It's because they have the same quantum numbers. So we can make a gauge singlet out of the lepton doublet and the Higgs doublet. So then we can put it together with another one of these. C is charge conjugation to get the charge to come out, right? And we have an operator that violates lepton number. And in fact, all of the odd numbered operators violate lepton number or baryon number. So I'll ignore those. Although this one is cool. You can use this one, this operator in neutrino physics if you're playing around. Yeah?
Sorry, isn't that maybe something that we want everyone to use in
Yeah, it's a very interesting operator. Absolutely, it is. Yes, it's just not something that you would fit at the LHC. You would look for it in neutrino physics and baryogenesis and something else. Yeah, there are a lot of papers on this. Yeah? Can you repeat that? I can't hear you. The question is, I'm supposed to repeat the questions. How can we see that that's a unique dimension 5 operator? And that is because the quantum numbers of these two guys are the same. There are no other particles in the standard model which have the same quantum numbers. So these are the only ones you can put together like this. So dimension 5 has to be 2 fermions, two scalars, right? So it's the only one. You could do it by exhaustion if you wanted. Okay, so that guy we'll forget, although it's extremely interesting. Okay, so we have a basis of operators here. It's called the Warsaw Basis. As Anish mentioned, it took many years to get this basis complete, and there are a lot of operators here. So let's look at a couple of them. Let me see here. Let's look at the ones in this column here. Here are guys that just have the Higgs doublet. So you have phi dagger phi cubed. That's the one we talked about before. We have things with covariant derivatives on the phi. What else do we have here? We have 3 gluon operators. Here's one, glue, glue, glue. The tildes are CP violating. Typically, we'll assume CP conservation, not for any deep and profound reason, but just because we're lazy. What other kinds of operators do we have? We have operators here, this column, phi dagger phi, g mu nu, g mu nu. And it started getting this effective Lagrangian to dimension 6 is take the standard model Lagrangian and just add phi dagger phi to every term. Phi dagger phi is dimension 2, so we just take the whole standard model Lagrangian and add phi dagger phi. Yeah?
So Anish was saying that to build a SMEF operators, one of the first things you do is you get rid of all your total derivatives. Has that already been done in the Warsaw Basis?
Yeah, actually, the reason it took so long to get this basis is that you can play around with all your operators. What are you allowed to do with your operators? You're allowed to integrate by parts. So you can integrate by parts and move derivatives around. The other thing is that you can do field redefinitions, as he was talking about yesterday. And at dimension 6, the equations of motion and the field redefinitions are the same thing. At dimension 8, that does not work. So when you get this basis has made all these field redefinitions, shifted everything around so that we got rid of as many derivatives as possible. So this is a unique basis where there's nothing that is related to each other by integration by parts or by field redefinitions. So it's not a unique basis. There are lots of other bases that people use. There's, for example, the Silch basis, which was very popular a number of years ago. You know, you can use whatever basis you want, but this is a particularly useful one. And it's useful because it's complete, and it's also useful because there's a lot of machinery associated with it. You can generate the Feynman rules automatically. There are codes which generate the operators and the interactions automatically. So this has all been put into the big picture framework. So a lot of the work is automatic, yeah?
Sorry, I think you just mentioned that we don't have any B or L solid.
I'm saying there's CP violating. Oh, the B violating at dimension 6. There are no L violating terms here, though, I don't believe.
Right, but the reason that we didn't consider that dimension 5.
We didn't consider the dimension 5 because it's lepton number violating. Delta L equals 2. Yeah. And we don't typically go beyond dimension 6.
Oh, okay.
I mean, you could. We know how to write down all the operators. But the dimension 7 ones would be lepton number violating typically. So, I mean, the reason you stop at dimension 6, I'm going to talk about dimension 8 a little bit, but you stop at dimension 6, A, from a practical point of view, and B, we're going to assume this scale 1 over lambda squared is really, really big. So we're going to hope that the next order in the expansion is really, really small. That's kind of the mindset that goes into these guys. So there are a lot of operators here, okay? We've got some which just add phi dagger phi. Those operators don't really do very much because they don't change the kinematics. They just add a factor h plus v squared, okay? So the really interesting operators here are the ones with derivatives. So the ones with derivatives are the ones that can change the kinematic structures of our experimental results and really give us new physics. So those are the ones that we're going to be interested in. Let's see here. Yeah, so most of these mini operators come from flavor. If you just look at one generation, you have way fewer operators. And this kind of table here, you can see here that they didn't put in the left-handed index just for simplicity. So L bar is the left-handed doublet, and whereas Q bar is the left-handed doublet. And for example, P and R and this guy here, these are flavor indices. So if you look at phi Q1, say, which is kind of an interesting term, it involves the Higgs. It's got a derivative here, and then it's got a Q bar gamma mu Q. So in general, that could have flavor indices. So it could be Q bar from the first generation and Q from the third. Typically, we ignore effects like that. Okay, so there are a lot of operators. Okay, but like I said, the power of this way of thinking of things is that it connects the physics in many different areas. So, for example, TTZ is, we have limits from top quark and from Electroweak when we make an Electroweak Z. When we make dibosons, I'll show you that the same operators contribute to WW production as contribute to Higgs goes to WW, which should be no surprise. So we can put it together. Okay. Yeah?
This is a really naive question, but don't the normal standard model operators give us all those processes that you were just talking about?
The question is, do the standard model operators give us the processes? And the answer is absolutely not. Because, well, the answer is, for example, in some of these, you could have things that connect different generations. You could have Higgs goes to tau e. That would be contained within this, unless I made assumptions. And the standard model processes would have different shapes. They would look different because of these contributions here. They would look different because they're operators with derivatives. So it's different, like flavor-changing operators, which maybe occur in the SMEF, depending on which things you put in, different structures. Yeah?
So if you have a non-derivative operator, is it just adding an offset to the cross-section without changing the shape?
That is a very good question. The question is, if you have a non-derivative operator, is it just an offset? And that is exactly right. So when you add phi dagger phi, say, to the standard model, all you're doing is adding, say, v squared to the standard model. So it's a shift. And I'll show you a specific example of that. So the new physics is in operators with derivatives. The old physics is just like generating a kappa, a shift. Yes? And that's a good way to think about it, actually, is that if I don't have operators with derivatives, I'm just packaging myself in a big framework. But I'm still connecting different sectors here. Okay, so what's the advantage of this? It looks really complicated, but this is a quantum field theory. It's now a consistent quantum field theory. It's a field theory that's SU3, SU2, U1 invariant. So this field theory is renormalizable order by order in 1 over lambda, or 1 over lambda squared, if you like. So at each order in 1 over lambda, I can calculate radiative corrections, and I can systematically improve it. It will have an infinite number of counter terms, because every time I start renormalizing, I have to go to the next order and the next order and so forth. But nonetheless, it is consistently renormalizable. So I can calculate the QCD corrections. I can compute the cross sections for some process without knowing what the high-scale ultraviolet physics is. So all of the new physics is contained in these coefficient functions. I might not know what they are, but I can limit these coefficient functions. And then the idea is, if I actually measured one of these coefficient functions to be non-zero, then I would go say, where could that come from? So that's kind of the logic here. So at this level, what I'm telling you is these SMEF calculations are model independent. I've got some coefficients. I calculate some process in terms of these coefficients, and it is what it is. So this sounds pretty good, but the question is, how does it work, and is it really model independent? Okay, so let's talk about the Higgs mechanism in SMEF. On Monday, I derived the Higgs mechanism in the standard model, and I calculated the gauge boson masses and so forth. And it shouldn't surprise you that this is just identical here. There's no magic. So the Lagrangian is just what I started with, d mu phi dagger, d mu phi, mu squared phi dagger phi, lambda phi dagger to the fourth. So here's the standard model. And here are all the terms which come in to talk to the potential. So these are all of the dimension 6 terms which only contain scalars. Okay, so you can see instantly that there's some problem here with the kinetic energy term, because the kinetic energy term is supposed to be normalized to d mu phi dagger d mu phi. That's how we normalize the kinetic energy term. So let's look at the CHD term here. So when the phi has a v, this will give me v squared over 2 times the kinetic energy term. So it will shift the kinetic energy term. This term here will also contribute to the kinetic energy term. So I have phi dagger, phi, d mu, phi dagger, phi. That's the CH box term. I can integrate by parts, and this goes to minus d mu phi dagger phi, d mu phi dagger phi. And then when I take phi goes to v plus h over the square root of 2, you can see that there's going to be a correction to the kinetic energy term from this guy also with the minus sign. Okay, so if I look at the other terms, the terms without derivatives, all I have to do is minimize the potential just like in the standard model. So I've got this guy here. So I take the derivative of the potential with respect to phi, I find the minimum of phi, and I look at the VEV. So here's the VEV in the SMEF. This is the standard model piece, mu squared over lambda. So note I flipped the sign here so that mu squared is positive. And then there's a correction from the C6 term, this guy here. So the VEV in the standard model effective field theory is not the same as the VEV in the standard model. It's got this extra piece. And this is a general feature of the standard model effective field theory. The relationships between the parameters of the theory are different in the SMEF and in the standard model. So here we have this extra piece contributing to V. Okay, so here's the Lagrangian. Here's the corrections to the kinetic energy of the Higgs. So there's a CHD piece and the CH box piece here. And then here we have the H0 squared pieces. So I need to get to canonical normalization, and I always do this in the SMEF. So I shift the Higgs field so that I get the canonical normalization. So the physical Higgs field is shifted by these factors here. So when I go on and show you some results for things like Higgs to BB bar, you'll see that you always have this factor of CHD over 4 minus CH box, because it just comes in from this normalization of the kinetic energy. Okay, so I just put it here. Other possible purely scalar operators, because there were only 3 on the last slide. At dimension 6, you can eliminate them by integration by parts or by field redefinitions. The equations of motion, which is how I do it because I'm lazy according to Anish, only works at dimension 6. But it gives you exactly the same answer. Okay, so there we are. So now we have to continue to construct our field theory. And I'm not going to do the algebra because it's only algebra. Okay, so in an identical fashion as in the standard model, I find the gauge boson masses. So I construct the kinetic energy d mu phi, and I multiply everything out, and I find the W mass and the Z mass. This is exactly the same as the standard model, except you have these extra operators. So the extra operators that contribute to the W and Z mass are these guys here, which I've written OHWB and OHD. We've already seen OHD is something that contributes to the kinetic energy, and HWB has derivatives in here. See, W mu nu, B mu nu. So when these phi's are both V's, you can see it gives a mixing between the SU2 gauge bosons and the U1 gauge bosons. So when I diagonalize the mass matrix, you can see you're going to have a piece from this HWB because it's got this mixing between the gauge bosons. Okay, so here's the W mass and here's the Z mass. The bars on here are just put on to remind you that the initial Lagrangian contains the effects of the SMEF, and so the standard model relationships are different. So that's just to remind you. So the W mass is the same as before, GV over 2. The Z mass is the same as before, but now it gets corrections from this CHWB and the CHD. So when I define my electroweak theory, and I have my 4 parameters, which I took before, mh squared alpha G Fermi mz. So now all these relationships are going to be different because I have to invert this. But that's okay, I know how to do this. But these 2 operators are nothing new. We know what these 2 operators are. So in fact, CHWB is just the S parameter. So it's a tree-level contribution to the S parameter. And CHD is just a tree-level contribution to the T parameter. So far, I haven't really done much new. I've got an S and T sort of put in by hand. So I put CHWB in, which is just like putting a term delta S in by hand. I don't know where it comes from, but I put it in there. And CHD, again, it's just putting in delta T. So what this is going to tell you is that when you start looking at limits on things, these particular operators are very well constrained because we've been limiting them from our data for centuries just by limiting S and T. So the question is, do I need to add radiative corrections plus this stuff? And the answer is absolutely yes. I'll talk a little bit about this because I said the SMEF was an effective field theory. And so I can calculate these radiative corrections. The QCD radiative corrections are known. They're in computer code. You turn the crank and your answer comes out. The electroweak radiative corrections are done on a case-by-case basis. And I've done a lot of these recently. And they're one-loop corrections, so everybody can do a one-loop correction. But they're kind of fun because they have things like these operators. So the vertices get very complicated because the vertices have all these factors of P's and so forth coming from the fact that you have the new interactions. So yes, absolutely, you have to do the radiative corrections, but they are not all known yet. So there's something for you to calculate. I can give you a whole list of ones to calculate. It's fun.
We don't know which dominates over the other.
I'll answer the question. The question is, how do we know which are going to be the important radiative corrections? And the answer is we don't know. But what happens when you do electroweak radiative corrections to something are a whole bunch of operators come in at one loop that weren't there at tree level, and then you lose a lot of predictive power. And this is a problem with this whole approach. And it's not a solved problem.
So, very naive question. Is the HWB dimension 4?
The question is HWB dimension 4? No, because there are 2 derivatives here. Okay, so 2 derivatives. So this is 2, 1 plus 1. Good question, yes. It's always good to count your dimensions here. Yeah. So sorry, W mu nu is D mu W nu minus D nu W mu. Yeah, I should have written it down, yes?
So when we write down the standard model EFT, which scale are we writing them down?
The question is, when we write down the standard model EFT, at which scale are we writing it down? And I'll talk about that in a minute, but the answer to that question is, the picture is that the standard model EFT is at my scale lambda, my very high scale, and then I will renormalization group evolve all my coefficients to MW. So, and then I'll do my fit at MW. I'll look at the data at MW, but I'll start up here where the standard model effective field theory is assumed to be matched to some UV complete theory. So these coefficients I haven't specified here, but they're taken to be at some scale lambda. Okay, so here's my first example of where using the standard model effective field theory is just a repackaging of the kappa framework and making it sound fancy. So this is the width of the Higgs to BB bar divided by the width of the Higgs to BB bar in the standard model. So in the original LHC analyses, this would just be 1 plus delta kappa b squared. So kappa b is 1 plus delta kappa b. This is the kappa framework. So I can calculate what this guy is in the standard model effective field theory. Here's my 1 over lambda squared. 1 over G Fermi is essentially v squared. So this is v squared over lambda squared. And there are a bunch of effective field theory coefficients. So the first two here, these are just from normalizing the Higgs kinetic energy in its standard form. Okay, so we know where those come from. These two guys here just come from the relationship, the change in the relationship between V and G Fermi in the standard model effective field theory, so they're not very interesting. They're just saying 1 over V squared is not, let's see, 1 over 2V squared is not G Fermi, I think, or whatever the relationship is. There's a correction to the relationship, which is these guys, and then you get a correction from the new dimension 6 operator. So this is the new piece here. But delta kappa b here just looks like a sum of a bunch of terms, no change in the momentum structure, nothing. So really, this is just a fancy way of writing the kappas as far as the fermions are concerned. So this delta kappa CDH, I wrote it here. It's phi dagger phi times the standard model Yukawa coupling. So terms like that, okay, it's the phi dagger phi times the standard model, so it's not too interesting. So here we have kappa b is just a bunch of this stuff. Nothing particularly new. Okay, so let's move on to something more interesting. So here's Higgs to ZZ, which, as you recall, was a discovery channel at the LHC looking for Higgs to ZZ. So here I have the width for Higgs to ZZ over the standard model width, and here's the width for Higgs to goes to Z FF bar, which is what we actually measure over the standard model piece. So it's 1, and then there's 1 over lambda squared, and there's 2 types of contributions. The first type of contribution, this little ck, is just this combination of coefficients which came into renormalizing the b decays. It's just numbers. Doesn't mean anything. But this second piece here, okay, CZZ, is written down here, okay? So I didn't write down these operators, CHW, CHB, CHWB, but they all have derivatives. So they change the shape of my prediction. So here, for example, you can see that if I make one of the Z's actually decay to FF bar, I get one coefficient, I get a different coefficient for on-shell Z's. So we're measuring some kinematics here. So how does this actually work? So the EFT actually has more information than just the total rate. And this is how we're going to get new physics out of it. So if I look at d gamma dq squared, where q squared is the invariant mass of these 2 outgoing fermions. So it'd be mz squared if it were on shell. Okay, so it's a standard model piece. And then there's just this constant rescaling here, as I showed in the previous slide. But then there's a piece which is q squared over lambda squared, some coefficients times a function. So this is generic in the standard model effective field theory, that you get pieces with the energy squared upstairs. So this is q squared of the 2 fermions. So it's a piece which is growing. So it's e squared over lambda squared. And this is typically how you look for EFT effects. You look for rather large q squareds or pt squareds, or you look in the tails of your distributions. And this dot 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 here is plotted here. So it's a function of the kinematics of the event. It depends on how they do the experiment, what cut they put on the lowest fermion pair that they can see. But you can already see this q squared is going to change how the decay looks, the shape. Okay, yeah, questions?
So when doing calculations like this, thinking about Anish's lectures and how he was talking about how you need to match the UV theory and the EFT. If we don't know the UV theory here, how does that work?
The question is, how can I do this if I don't know the UV theory? But that's the whole point of the SMEFT. I don't need to know the UV theory. These coefficients are just arbitrary. They're just coefficients. I put them in. I don't need to know what's happening. And that is really the power of the SMEFT. It's just an effective Lagrangian in terms of these coefficients. So I am not yet matching to any high-scale physics. Anish was talking about, okay, I'm at the UV theory, I've got my effective field theory, but I want to match to the underlying theory. And that's the next step, right? Because I'd like to say, I know what my underlying theory is, and then I can calculate what these coefficients might be. But a general analysis of this just depends on arbitrary coefficients. They might or might not correspond to some underlying model. Yeah?
So then just to follow up, so the idea here is that we use the data to sort of like determine the coefficients?
Absolutely. I'm going to show you lots of plots. The whole point is we use the data, we make a limit on these coefficients, and then we say, aha, does that correspond to my favorite model? So the hope is, at the LHC, they'll find some coefficients which are not zero. So you measure a coefficient that's not zero, and then you look at your whole space of UV models and you say, maybe it's that model. Because as I'll show you, different models have different patterns of coefficients. Yes?
When you try to constrain your coefficients, do we have to fix that?
The question is, can you try to constrain your coefficients? And I will answer that. Because as I showed yesterday in the Singlet model, you only get a couple coefficients. I'll show you an example of the 2HDM and show you that you get different coefficients than in other models. So yes, so the way you do your fits is you would do your fits saying, aha, I'm thinking in the back of my mind that I've got a 2HDM and it's going to generate these coefficients, and I'll do it that way.
And the lambda will be fixed. If you have to fix
I'll answer that question. The question is, do you need to know lambda? And actually, you can all answer that question already, right? You can all answer, do you need to know lambda? Because this particular slide is gluon fusion, but they're all the same. Because remember, the effective Lagrangian is coefficient over lambda squared. So you only measure coefficient over lambda squared. So you don't know lambda, you don't know the coefficient, you only know the combination at dimension 6. So when you say, I fixed a scale, that just means that you fix the coefficient. So you measure the ratio. Okay, so something interesting happens in these models, or in this approach, and I'll show you gluon fusion here, but it's a generic thing. So the operators that contribute to gluon fusion that I was talking about yesterday, or Monday, I guess, glu goes to H. So they're just two operators that would contribute to gluon fusion. There would be this CHG, which is, again, one of these phi dagger phis on the standard model piece here. And then there would be this CTH, which was, I had CBH before, which was renormalizing the B quark Yukawa. This is renormalizing the top quark Yukawa here. And this is generic in these theories, that it changes the relationship between the top mass and the Yukawa. Remember in the standard model, if I diagonalize the Yukawa matrix, I was diagonalizing the mass matrix, and I was also diagonalizing the Higgs couplings. But that's not true here, because here you can see that the mass of the top is Yukawa, just as I had before, but then it's got a contribution from this new operator, CTH. So you put these phi's, you make them v's, and you get a contribution here. So then when I invert this, the coupling of the top to the Higgs is different than it was before. So you can't simultaneously diagonalize them typically. So you have a different relationship for the top quark Yukawa with the mass. But that's okay, we know how to do this. So for example, in gluon fusion, you can ask the question of what do we actually measure? How do we look at gluon fusion in the standard model effective field theory? And this is a classic example here, because if I'm going to calculate glu goes to Higgs, and I'll just calculate in the MT goes to infinity limit, because that's a good approximation. I don't have to. I can do the real thing. So I have the standard model amplitude for glu goes to H1, and then I have a contribution from this effective GGH operator here, and I have a contribution here from messing with the top quark Yukawa here, so I can only measure this combination of SMEFT coefficients. And this is typical in the standard model effective field theory, that you get lots of blind directions, that a given measurement will be dependent on a certain combination of coefficients, and that you can't separate them out. And we call these blind directions, because if I just measure gluon fusion, I'm only measuring this particular combination. Okay? And so it's not very interesting. But now I can go back. Okay, if I look at this, G mu nu, okay, within here, there will be 3 gluon operators too from the G mu nu piece. So I also have a contribution from CHG to glue goes to glue H. Okay. So I can look at glue goes to glue H in exactly the same framework. And now I see the same generic thing in the standard model effective field theory that I saw in the zeta case. I see a dependence in the amplitudes on pt squared over lambda squared. Yes?
When you remove all the redundant operators, you're saying
Oh, the question is, are there other operators that would contribute to glue goes to glue H?
I thought removing all the redundant operators removes your flat directions.
Oh, adding new processes will remove the flat directions. So if I measure glue goes to H, there is a flat direction here. Okay?
And that's an independent statement from the Warsaw Basis being all independent operators.
That is independent. That is saying that that process depends on one combination of operators. And I will show you how you break that degeneracy in this particular case. But it occurs over and over and over again in standard model effective field theory, that a given process will only measure a certain combination of operators. So you see it in this also. So now I'm looking at the same 2 terms in my effective Lagrangian, modification of the top quark Yukawa and modification of the glue H coupling. And I can look at glue goes to glue H, so this is Higgs plus jet production, which is measured excruciatingly well at the LHC. And now the SMEF will give me operators which depend on pt squared over lambda squared. So if I plot the pt of the Higgs and go out to high pt, what this plot does is it turns on these 2 different coefficients. You still can't separate out which is which, but you can see that at high pt here, you're starting to get rather large effects. And the values of the coefficients that are chosen in this particular plot are chosen such that the total rate for Higgs production comes out to be the experimental rate. So yeah, if you go to high PT, you can get these effects. They're sort of order, well, they're less than 10, but they're order 5. Yes?
Is the reason that the new physics effects show up at high PT because the top mass approximation is no longer valid?
The question is, do the new physics effects show up at high PT have anything to do with the MT goes to infinity limit? And the answer is absolutely not. The reason is that we're looking at dimension 6 operators. So the dimension 6 operators, okay, so you have dim 6 over lambda squared. So to get your calculation right, you either have effects which go like b squared over lambda squared, or which go like pt squared over lambda squared, just to get your dimensions right. And typically, they're pt squared over lambda squared. And that is why you always go to the tails of things when you're looking for new physics. Yes?
If you're looking at the tails of distributions and these start becoming larger, don't you have to start worrying about dimension 8 operators?
The question is, when you go to the tails, don't you get into problems with the effective field theory being valid? And the answer is absolutely yes. And the answer is that's one of the complications of these theories, is that you have to be in a regime where your dimension 6 contributions are smaller than your dimension 8. So you can't take pt squared of 3,000 or whatever and think it's going to be valid. Yes, and that's the fun and the not so fun and the complication. Okay, so let's just finish up with this example with the 2 operators. So we had glue goes to H or glue goes to HG, depends on a combination of operators. And how would you break that degeneracy? Well, you would break the degeneracy by looking at a different process. And that's always what happens. In this example, I'll look at glue goes to TTH. So here's TTH. So this guy only depends on the rescaling of the top quark Yukawa. So by measuring the 2 processes separately, I can learn about the two different coefficients. I got two coefficients, I got two processes. It's not a surprise. So here we go. Here's this GGH coupling, and here's the TTH coupling. And you can see here's the limit from top quark associated production, TTH, only depends on the one coefficient, whereas the glue H depends on a combination. And you put them, no, I don't want to do that. And you put them together, and you see that excuse me. Let me get rid of all notifications about self-care. That's good. I'm sure it's good. So you put them together, and you get a limit on the coefficient. So you can see that to actually limit all of these coefficients, you're going to need a whole bunch of processes. That's the bottom line here. Okay. So you ask about when is the EFT valid? And oh, this is complicated, and people have been fighting and fighting about this, and nobody knows the right answer. So here is the issue about when is the EFT valid. So I've got my standard model Lagrangian, I've got my dimension 6 operators, and I've got my dimension 8 operators. So I'm going to calculate some cross-section, which is an amplitude squared. So here I have my standard model cross-section plus my A6 squared. That's just going to be the guy that comes from my dimension 6 squared over lambda squared plus blah, blah, blah. So here are the dimension 6 terms, just the square of this guy, okay? So thought number one, I'm doing an expansion in orders of 1 over lambda squared. So really, I should only keep the 1 over lambda squared piece here, okay? So if I keep only the 1 over lambda squared piece, I'm not calculating an absolute amplitude squared. I'm calculating the standard model piece plus an interference piece, not the full amp squared. So if I only keep this guy, I'm doing a consistent expansion in 1 over lambda squared, but my cross-section isn't guaranteed to be positive because I'm only calculating part of the cross-section. So that's not too good. On the other hand, if I include this piece, the A6 squared over lambda the 4th piece, well, now I'm calculating an amp squared, and it's positive, guaranteed to be positive definite, but now the observant here will say, this is 1 over lambda to the 4th, and these dim8 pieces that I threw out, they're also 1 over lambda 4. So really, guys, it's not fair to keep these guys and leave these guys out. Okay, so that's the argument. So let's do some counting. Let's say that maybe the standard model piece has some typical coupling. We'll call it G standard model. And let's say that the dimension 6 has some typical coupling. We'll call it GBSM. So in that case, I'll put coupling constants in front of all of these guys. And I'll say, well, here's my standard model piece. It's going to have a G standard model squared. Here's my interference piece between the standard model and the dimension 6 at 1 over lambda squared. It's going to have a standard model and a BSM coupling. Here's my dimension 6 squared. It's going to have a BSM squared piece. And here's my dimension 8 interfering with the standard model. It's 1 over lambda to the 4th. And it's going to have it's going to have a power of BSM coupling and standard model coupling. So if these couplings are sort of the same size, then yeah, all these terms are sort of the same size, then you have to include them all. But maybe I'm in some strongish coupling regime where these BSM couplings are much bigger than the standard model pieces. And so if the BSM piece coupling is much bigger than this guy, the A6 squared is much bigger than the dimension 8, and it would be okay to drop the dimension 8. But now we're getting into the regime of putting assumptions into what's supposed to be a model-independent approach. Okay, so I mentioned that this approach, you can't just use one sector of the theory, and let me illustrate this with the Higgs couplings to gauge bosons. So I want to couple the Higgs to WW pairs. So there are two operators here that affect the Higgs coupling to WW pairs, or to ZZ for that matter. So they've got the covariant derivatives of the SU2 gauge bosons and of the U1 gauge bosons, OW and OB, and I also wrote down a term with 3 W's, which will arise when I'm considering WW pair production. So the effective field theory, as I said, is going to be enhanced at the high PT. These are derivative interactions, and so they change the shapes. Yes?
This is probably a stupid question, but the D sub 5 is a D5, right?
the question is, did I make a typo here? And I noticed it this morning, but I was too lazy to retech it. Yes, yes. There is a typo here, and I didn't feel like retyping. But yes, this is obviously d nu phi, right, to make the indices come out right. I'll fix it later after I've had a cup of coffee. But okay, so you can't just fit the Higgs couplings because there's this whole mess where everything comes in. So if I have Higgs to WW, I also have to look at QQ bar goes to WW with Z and gamma exchange. So all of these things depend on the same couplings, right? So I can start to do something that's called a global fit. And what I mean by a global fit is when I look at things in different sectors of the theory. So here I'm going to look at Higgs decays, and then I'm going to look at WW decays, because I'm going to say that this red blob and this red blob contain contributions from the same operators. So now you should remember from unitarity. Remember I showed you the example of E plus E minus goes to W pairs from LEP. And what you should have learned from that example is if you mess around with the ZWW and the gamma WW couplings, you spoil these unitarity cancellations. So again, in this process, you're spoiling the unitarity cancellations because you're messing around with the effective 3-gauge boson vertices by adding these new effects from these Smith operators. Okay? Yeah?
I don't understand how to get a QQ gauge boson vortex from the previous two operators.
Oh, these are different operators. Yes. I said anomalous QQZ vertices too, and they come from different standard model effective field theory operators. Absolutely. So
you're looking at the final state.
the question here is, what about the blob on the initial state? So when we do the fits, we will put in all of the effective field theory operators that contribute to the process. And there are actually 7 effective field theory operators that contribute to this process. So it's the operators I wrote in the previous page that contribute to this vertex, but there are further operators, which I won't talk about for lack of time, but further operators change the QQZ vertices. So for example, if I go back to the LEP data and look at the Z decays to QQ bar and the Z decays to BB bar, they will constrain the operators that affect the Z decays. So it's all mixed up. All of our processes that we look at get contributions from many of these operators. So Higgs physics is no longer in a world by itself, but it lives with all these other things. But now I want to show you a plot that always gets people excited. So here's a standard plot you might derive when you're using the standard model effective field theory, which shows you how many things go wrong in this approach. So what this plot is, I'm looking at PP goes to W plus W minus. So QQ bar goes to W plus W minus as a function of the PT of the W. Lots of orders of magnitude on the y-axis. So the black line here is just a standard model prediction. The blue line that's kind of overlapping the black line includes all the radiative corrections, and they don't do much here. Okay, so now you say, let's try to do this in the standard model effective field theory. So let's put in some values for these coefficient functions that we know aren't ruled out by other data. So we'll pick some random values, and I'll just tell you the random values I pick are not ruled out. So then I'll expand things to 1 over lambda squared, and this will be a very nice expansion in powers of 1 over lambda squared. So that is this blue dashed line here, and you can see right here it goes negative. So what does that mean? Well, if I'm getting a negative cross-section, it means my expansion is no longer valid. I simply can't do it here. So I better cut it off somewhere down here. So one approach for dealing with this would be to say that I'm just going to always have an upper energy cut on my analyses in the standard model effective field theory such that I don't get negative cross-section. So I'll just cut it off somewhere like this. And that's fine, but then the experimentalists will come back to you and they'll say, okay, you want to put a cut on the theory based on the fact that we can't have negative cross-sections. But hey guys, isn't this going to be different for every process I look at? Well, how does this make sense? So the experimentalists really don't like the idea of putting an upper cut on this because, you know, it's going to be different for example, for WZ, I'd have to put a different cut on for where this goes negative and so forth. So this is not so good. So the experimentalists come back and they say, well, can't I just calculate the amp squared, the 1 over lambda to the 4th pieces? And so here's what happens. So these curves here, the green and the red, are what happened when I put in some anomalous couplings and just calculate the amp squared. So this will have 1 over lambda to the 4th pieces, nice and positive. But what you should notice here is look at the orders of magnitude here. All of the power of the fits that you are seeing coming out of the LHC and other places are coming from the tails here. They're coming from the 1 over lambda to the 4th pieces that are coming here. So then you really have to face the question of, does this make sense, just doing the dimension 6 analysis? So this is an open area of active debate in Smith fits. Is this versus this? Yes?
On the plot, it seems like it goes very small, but not negative. The number is 10 to the minus.
The question is this really negative? And the answer is yeah, it's just the way I plotted it. It's absolutely negative. It goes boom, it goes negative, absolutely. Yes, it really does. And so that it's telling you something. So now we see that this beautiful theory, just a second, I'll answer your question, was supposed to be model independent, but it's not really. Yes? The question is, how many terms am I including? I am including the full amp squared. So it's a standard model plus dim6 quantity squared, absolute value quantity squared. Yes, there's another question?
Yeah, what's the sort of the whole magenta line?
The question is, what is this line down here?
Yeah.
Oh, this is just putting in a different set of anomalous couplings at 1 over lambda squared. So this one that goes negative has the anomalous couplings that affect the 3-gauge boson vertex only, so it just shows those. And this magenta, this purplish line, has only the anomalous couplings that affect the gauge boson vertices. And the reason that the ones that affect the fermion vertices don't do as much as the ones that affect the gauge boson vertices is that changes to the fermion vertices are very highly constrained by the precision electroweak data at LEP, where we looked at Z goes to BB bar, Z goes to CC bar, and so forth. So those possible changes are very highly constrained. And so this plot has data that's allowed. So, yes, another question?
Yeah, thanks. So if you're not making the assumption that the standard model coupling is the same order as the BSM coupling, who's to say there's not something at dimension 8 that would sort of fix this problem with the blue line?
I am not making any assumptions here, and I will show you some stuff. The question was, what couldn't dimension 8 fixes? And of course, dimension 8 changes things, but we have not yet done full analyses of dimension 8 couplings. There are just way too many of them to do this kind of study. So that's another active area of research. Okay, so now assumptions are creeping into our beautiful global fits here. So this just is an example of where these assumptions are creeping in. So this is a fit just to Higgs data and diboson data at the LHC for W pair production, WZ production, WH production, and ZH production. And what it shows, what you're supposed to learn from this, bunch of coefficients, you don't really care what the coefficients are, but what it shows is that how the fits change when you go from 1 over lambda to the 4th, so 1 over lambda squared plus 1 over lambda to the 4th, as opposed to the linear approximation, and then when you put QCD corrections in. So depending on how you do your fit to the various coefficients, you're going to get slightly different answers. All right, let me skip that. Okay, so here we go. Lots of things. So this is what you get out of these, and you look at this and say, oh, well, who cares about this? So there are a number of groups who are doing global fits to the data. And so this particular fit has the data from top quark production, from Higgs production, and from diboson production. It does not have the limits from the LEP Electroweak precision observables. And the first thing you'll notice is they fit to a gazillion coefficients here. I think it's about 30 in this particular fit. Doesn't matter what they are, and I think they intentionally write it so you can't see it. Okay? I mean, you really have to stare at these things and think, oh, what is that? But what you're supposed to learn from this plot is that there really is a difference in using the 1 over lambda squared or the 1 over lambda to the 4th approximation. So the orange is the fit's using the 1 over lambda squared approximation, and the blue is using the 1 over lambda to the 4th approximation. So you can see that depending on how you do your fit, you get quite different answers. And again, they plot c over lambda squared, so it's only that combination that you get. So you can't independently say that this probes a certain scale. But what you learn is that it's very different depending on how you do your fits. And you also learn from this that some of the things are very well constrained. This particular operator that's well constrained is one of the things that's, let me see which one that is. Yeah, I think that's the thing that corresponds to the t parameter. So that's very well constrained. But some of the stuff is barely constrained. And I pointed out that this fit also includes the QCD corrections. They generate them automatically with the code that we have. Okay? So what are those two blue dots? I have no idea. What are those? I have no idea. Sorry. Okay. So here's another fit from a different group, okay? And you're supposed to learn different things from this group. And so what this group did is they included top Higgs, when I say EPO, EWPO, that's Electroweak precision observables, which is essentially the LEP data plus the WMAS. So that's a standard abbreviation, and the diboson data. So it's pretty much all the data that contributes to these operators, and different operators contribute to different things here. And so the top fit, you can see the effect of including the top data and not including the top data, because of course it's a lot more work to keep including more pieces. So the different colors here are top, no top. And you can see that for some of the, yeah, you have to really stare at this. For some of the operators, it makes a huge difference including the top data. And for a lot of the operators, it simply doesn't matter. So you can stare at this and say, yeah, for some things I really need the top data, and for some things I don't. And again, you can see orders of magnitude. You can see this is typical on these plots. It looks like they're all the same, but this guy's got a 10 to the minus 2, this guy's got a 10 to the minus 2, and this guy's got a 10. So it's orders of magnitude difference in how we constrain different things. Yes?
So imagining a scenario where there's a discovery and one of these coefficients is something really new and crazy, that coefficient is going to participate in so many different interactions, right?
The question is, if they find one coefficient that's new, is it going to participate in lots of things? And the answer is maybe. It depends on the coefficient, because some coefficients participate in many different processes, and some coefficients only participate in one. So it really depends on the discovery. So the other thing you can get from this bottom thing here, is they tried to plot a scale. So they set the coefficient function equal to 1, and they plotted a scale. And if you have the coefficient function equal to 1, that's the solid curves here. And it says that, well, we're probing a scale of about a TeV. So at the present time, we're not probing a very, very high scale. This top curve here is if you set the coefficients equal to 4 pi, which, I don't know, some strongly interacting theory, and you might probe a higher scale. But you really can't say too much. Okay. So the Electroweak corrections are done on a case-by-case basis. The QCD corrections are all known. But the running of the operators from the high scale lambda down to MW is something that Anish and collaborators spent a very long time doing, and it's a solved problem. So all coefficients run, everything in a quantum field theory runs. So these coefficient functions are matched to my UV complete theory at the scale lambda, and then they run down to the scale mu with these anomalous dimensions here, which are all now computed. We know what they are. Yes?
Why are we doing this running? Because in principle, all these coefficients are arbitrary. I don't have a matching, right?
But I'm going to tell you. The question is, why bother with the running? I'm doing my fits at MW, so who cares about the running? And that's a very good question. And the point is exactly this slide. The point is that these coefficients are defined at the scale lambda. And at the scale lambda, I'm going to predict what the coefficients are in terms of my model. So I'm going to say, I've got a 2HGM, so coefficient 1, 2, and 3 is this. Or I've got a singlet model, and coefficients 4, 5, and 6 are this. So if I'm matching at the high scale, then I run them down to NW, and then I do my fit. So I can do my fit and try to see if there's anything funky going on, and then try to work backwards. I mean, it would be easier to work this way, but we don't know how to do that. So we're working this way. We're doing our fit, then we'll renormalization group scale them up to the high scale and see where they came from. So that's the logic here. Because these fits by themselves, are you listening out there in Zoom land? These fits are boring. I mean, they're really boring. They're only interesting if they tell us something, if we find something, you know, non-zero that then we can try to interpret in terms of some model of UV physics. And it's a really hard way to learn about UV physics, right? You got to do these fits. There are all these problems with, you know, 1 over lambda squared, dim 8, blah, blah, blah. But it's the only way we know how to do it. It's the only game in town unless we discover something from a specific model. So the idea is that we match up here at the high scale, we renormalization group run down to the low scale, and then we do our fits. Okay, so the renormalization group running actually changes the fits quite a bit. So these SMEF coefficients are defined at the high scale, but the running of these coefficients might change the picture. Because suppose I had my singlet model that I was talking about yesterday, where I generated just 2 of these coefficients. I generate these coefficients at the high scale, but then I renormalization group evolve down to MW, and I generate a coefficient which in this case is CHD, which you should remember is essentially the T parameter. And the T parameter actually is fairly highly constrained. So even in the singlet model, which doesn't depend on the T parameter at the high scale, it does at MW through this renormalization group running. Okay, so now you say, what's all this matter? So here is the dream that of how this would work. It would say, well, I've got some model in the back of my mind, so I match this model to the SMEF at the high scale. I generate these coefficients, I run down, I do my fit, and I see something. Okay, so this is a singlet model. It's not particularly a great model, but it's simple. So here are the coefficients that it generates at high scale, CH box. So we'll do a global fit to Higgs data, to diboson data, by which I mean WW, WZ, Electroweak precision observables, LEP data, and then we'll get some combined limit within this green blob. So this is a limit on these arbitrary coefficients when I just let the 2 of them be fit. So I haven't yet said it's a singlet model. What I've said is I'm going to assume only these 2 coefficients. But then within the context of this model, and it works the same in all the models, within the context of this model, you can only be on these lines here. Okay, so I'm only like sort of at the edge of being allowed here. So that's how the study would work. And since I only have a few more minutes, I'm going to show you something about dimension 8. Let me see. Let me go forward and say, well, you want to see if these dimension 8 pieces are actually relevant. And so there's 2 ways to look at the dimension 8 pieces. We now have a complete catalog of all the dimension 8 pieces, so I could just pick some random coefficients and see what they do to, you know, the price of eggs in Kansas. I call that the agnostic approach. Pick some coefficients, see what the dimension 8 things do, or I could pick my favorite model and see what the dimension 8 things do. This is 2 different ways of trying to get a handle around whether we need these higher order terms. So, okay, so here's the agnostic approach. I'll say, let's look at a process. This particular process is W plus Higgs production. I'll calculate it CHW is one of the dimension 6 operators, and then I will put in dimension 8 operators, and I'll play around with them to try to get the biggest effect possible, consistent with the expansion being valid. Okay, so that kind of gives you like between the black band and the dotted band. So this is a change in the rate in WH production by messing with the dimension 8 operators randomly. And you can get sort of 10%-ish effects by this. So that says that, well, maybe it's possible that these guys matter. The other approach is pick your model, do the matching at the UV scale, do the fit, and see if dimension 8 matters. Oh, okay. So I'm just going to show you the 2HDM plot. So here's a 2HDM plot, including dimension 8 operators. It's kind of a teaser plot. Of course, in the 2HDM, I can make my model, and I can absolutely calculate the predictions and the limits. So the 2HDM in the Higgs sector depends on two parameters. It depends on cos beta minus alpha and tan beta, where alpha is the angle that diagonalizes the two Higgs doublet mass matrix, and tan beta is the ratio of VEVs. And there are different assignments for the fermion couplings. This is a particular one. So how would I do this? So I would take the 2 Higgs doublet model, and I send all the masses to infinity. So this is going to be my decoupling limit. And then I would match to the SMEFT. And what happens when I match to the SMEFT is that this parameter cos beta minus alpha is 1 over lambda squared. So my dimension 6 operators go like cos beta minus alpha. So here we go. Here's a fit to Higgs data. The red is the exact line. These flowers going out here are the matching to dim 6. And the blue line here includes the dim 8 terms. So here is an example where you absolutely have to include the dimension 8 contribution in order to reproduce the whole model. So that's kind of the state of the art of the dimension 6 stuff, because the dimension 6 and the dimension 8 stuff, we don't actually know. I can't tell you this is when it's important and this is when it's not important. I can say that we have some examples that suggest that it might be important. You had a question?
Yeah, thanks. So looking at the left side of this plot, it looks like when you go to the 1 over lambda to the 4th, the prediction actually gets a little bit worse.
It's indistinguishable here. It's not a prediction, it's a fit to data. And you can say it's indistinguishable. The 1 over lambda squared, 1 over lambda fourth, doesn't really make much difference here. The important point is you can't reproduce the physics using only the dimension 6 standard model effective field theory. And so now I have to keep up my reputation of always ending on time. I have to say that in Higgs physics and in SMEF physics, there's a huge amount of important and interesting stuff for you guys to calculate, and I hope you're just going to go for it and keep calculating. So that's it. Okay. Questions? Yes?
I'm a little confused about the cross-section being negative statement. So if I understand correctly, you found that for some coefficients in the SMEF, then you get a negative cross-section, but in entirety that cannot be. Therefore, aren't those coefficients theoretically disallowed?
The question is, what's it mean when you get a negative cross-section? That means your expansion is no good, right? Because you know that the cross-section is positive. Your expansion is no good, and so those coefficients are no good. You're in a regime where the approximation of taking just the interference term is absolutely not a good approximation. So those coefficients are ruled out, and that energy scale tells you that you should be working at lower energy scales. Yes? So typically in the fits, they just throw out the negative cross-section terms. They do a big scan over all these coefficients, and they just throw them out. But yeah, it's bad. No can do. Yeah. Yes? Yes?
So when doing the fit of the SMEF, we are doing the combination of the coefficient and the lambda square, right? But after the fitting, we need to evolve up to the scale of lambda. So do we need to make an assumption?
The question is, what about the fit and the evolution, right? So for example, in this fit, we did do that exercise, the fit and the evolution to the high scale. Typically in the fits, they don't do that. So you only evolve to the high scale if you're going to do a matching, right? If you're just going to do an agnostic fit to all the coefficients, you're at MW, and here are the coefficients at MW. If you're going to try to interpret these coefficients in terms of model parameters, then you have to evolve them to the high scale. And yes, this was done, for example, in this plot. And in fact, I don't have it here, but I could show you a 2HDM plot, which shows that it completely goes wrong if you don't do the renormalization group evolution. It's very, very important. Yeah. Yes?
Regarding the negative cross-section, do you expect something similar to happen once I include dimension 8 interference terms?
Oh, geez, you guys got all the right questions. Where are we? Where's some dimension 8 interference terms? I wrote them down somewhere. So whenever you only include the interference terms, you are not calculating an amp squared, and you could get into a regime where you get negative cross-section. So, but on the other hand, in order for this expansion to be valid, somehow you think you're in a theory where maybe the coefficients are smaller at dim 8 than dim 6. But absolutely, it's absolutely 100% possible that a random scan of dim 8 interference with the standard model, which has only been done for a couple cases. I showed you the WH case. Could get negative cross-sections again. Yeah, it's a problem that you're always going to get, and that you have to think about whether you're in the regime of validity of the theory. And the negative cross-section is just a statement that you're not in the regime where it works. Yeah?
Maybe a quick follow-up to that then. Are we expecting this breakdown to move higher up in energy with the dimension 8 operators, or is this...
Well, the question is, are we ever going to solve this problem? And the answer is that, well, the dim 8 terms are 1 over lambda to the 4th, and the dim 6 terms are 1 over lambda squared. So you expect that at each order, they're going to get smaller and smaller, these problems, because right now we're taking lambda to be typically a TeV. But if you took lambda to be 2 TeV, these dim 8 terms would be really, really small. And so it wouldn't matter what you did with them, because they'd be so small they wouldn't do anything. And in fact, one of the studies that I did with some postdocs, we looked at TTH production, where we looked at the dim 8 terms, and the dim 8 terms were nothing. Okay, you had a question?
Yeah. So how is this sort of different from standard perturbation? Like dimension 4. So if I calculate my amplitude to alpha squared, right, I'll get a alpha cubed interference term, and then if I don't include the alpha to the 4th term, I don't have my full amplitude squared. So then why should
Oh, the question is, how is this different from standard model perturbation theory? Well, in standard model perturbation theory, we know, or we hope we know, is that alpha cubed is smaller than alpha squared and so forth. So we're expanding in a small parameter, right? However, in the SMEF, we are not really expanding in a small parameter, because we're expanding in PT squared over lambda squared in many of these calculations. And so that's really the difference, is that there's an energy dependence that goes in there. So the expansion is not the same. Yes?
If the PT squared starts becoming the order of the lambda squared, don't you start being able to produce resonances of the new physics directly and constrain it that way?
Well, then it's not the SMEF. Then it's some strongly the question is, sorry, if the PT squared is on the order of the lambda squared, aren't you making heavy resonances? Yes, and if you go to PT squared on the order of lambda squared, the expansion is no longer valid because I don't have a small parameter. And then I'm in some different theory. I'm in some strong coupling theory. Yeah, right, that was what he said. And that's cool. If we see resonances, row resonances or something, yeah. It's not the SMEF, but it's very exciting, yeah. And you had a question.
we saw a negative character indicating that the theory had broken down at scale? We had to include more stuff or fix it somehow.
No, I didn't say that we had to include more stuff. I said, and this is actually a very important qualification here, once you get this negative cross-section, the approximation is no good. Including more stuff won't fix it. You have to go to lower energy, where this doesn't happen, where your theory is convergent.
Are there other indicators that we might see that are not just a negative drop-off like that?
Well, what happened, the question is, can we tell that we're approaching this regime where the expansion is no good? Well, what happens is that if you constrain stuff really, really well, you get a good constraint from the 1 over lambda squared terms, and they're always really small. So your perturbation theory is great, and you don't have to worry about this. It's only when you don't constrain stuff very, very well that you get into this sort of conundrum of which pieces to include. Okay? Yes? We should stop. Coffee.